I've been shopping for a new battery charger. I have the venerable AccuCell 6 50-watt charger, and I like it. And as you know from the video I posted some time ago, I do parallel charging with it, and it does everything I need it to do, but it doesn't do it very quickly. If I have four of my 1300 milliamp hour 4S batteries charging on it, it can like barely hit a half C, which those batteries can easily charge at 1C and maybe even 2 or 3C if you really wanted to push it. But it just cannot push the power to get that done. And that's a little, I don't know, that's a little annoying. So I've been thinking about getting a more powerful charger. And as is usual, whenever I'm thinking about something, I make a video about it and I tell you about it because, people seem to like when I do that. So I'm going to take you through a little bit of an introduction to battery charger specs and fundamentals. And then I'm going to do a second video where I'm going to do a little rundown of some battery chargers that I've been looking at. And, people liked when I did that with the flight control board, so maybe you'll like when I do that with battery chargers. Let's get into it. If you're going to understand the specs for a battery charger, you must understand the relationship that I'm showing on this slide. Watts equals volts times amps. Okay? If you don't have an intuitive grasp of what those things mean, then I find that fluid, like hydraulics or plumbing, is a very intuitive way of thinking about electricity, as long as you don't go too far into the analogy and end up saying something incorrect. But people have an intuitive understanding of how fluid works because we've all put our thumb over the end of a garden hose and made it squirt out, right? We've all experienced plumbing all of our lives. We know that water flows downhill and all these things, right? So if you want to think of volts as water pressure and amps as water flow rate, that would not be an inaccurate way of thinking about those things. So here in the lower left, this is a cutting jet, a water jet cutting tool. It has an incredibly high pressure jet of water shooting out of it, and it's cutting a piece of steel. No kidding. If you weren't aware that this existed, go look it up. It is super cool. And it is a very high pressure, but not a very high flow rate. Very little water is actually coming out. It's just coming out at a very, very high pressure. And that is an example of maybe a high voltage, low amperage scenario. On the flip side, I have here a drainage culvert, and that's an example of a high flow rate at low pressure, okay? High amps, low volts. Okay, so those are two ways of conceptualizing those things. Notice that depending on the ratio of volts to amps, in both of these cases, we might have exactly the same number of watts. We would just have it distributed in a slightly different way. What are watts? When you think about watts, watts are the capability of the electricity to do work, okay? So, let's say that I'm going back to the previous slide. Let's say that I have a water wheel that I want to turn, okay? I could do that by pouring a lot of water at low pressure until the weight just gets so heavy. Think about like a river flowing by, right? A river is not very high pressure, but if you're up to your waist in a river, it can just have so much water pushing on you that it can knock you over, okay? Now think of something like a very, very high pressure garden hose, like a fire hose, right? A fire hose is not a fire hose actually is putting out quite a volume of water, but not as much water as that river. But it's putting it out at a very high pressure. And both of those things, I could shoot the water wheel with a high pressure, low current flow, or I could dump a low pressure, high current flow on the water wheel, and either way I could get it turning, okay? Go with that. The idea is that as long as the watts are the same, you can get the same amount of work out of the electricity. So you could have high volts and low amps. You could have low amps and high volts, and you could get the same amount of watts out of it. Watts do work. Amps make heat. Now this can be a little confusing because if you talk about the heat dissipated by a resistor or by a wire, it will be given in watts. Heat dissipated is given in the unit of watts, and this is a little confusing, and I don't want to go into that too much because I feel like it's a little bit of a distraction. But basically, when you're assessing the amount of heat that a given electrical circuit is going to sustain, that is calculated based on the amps going through it. And this is why you folks over in countries that use 240-volt electricity can have thinner wires in your walls and still get more power out of your electrical receptacles. You can have a 3,000-watt tea kettle, and we in America can't get that. And the reason is that in America we only have 120 volts. So we have half the volts. So we need twice the amps to make the same amount of watts. Twice the amps going through the wire means twice the heat generated, and that's the limiting factor on how much current. That's why you have a 15 or a 20 amp breaker, if you're in the US anyway, in your breaker box. The goal there is that if you were to pull more than 15 or 20 amps, then you would dissipate so much heat into the wires that you could have a fire hazard, okay? So amps make heat, watts do work. And what that means is that because of the relationship, volts times amps equal watts, higher volts means you can have lower amps and less heat for the same amount of work, okay? So 240 volts gets you more watts for less amps, and therefore less heat is generated. Well, that's good, right? So why don't we all just use a 400 volt or 1 kilovolt electrical circuitry, right? And just have very, very low amps with less heat. Well, the reason for that is that higher volts are also much more dangerous to humans, and at a certain point, you don't want that. But that is one reason, and again, this is a complex topic that we won't go off on a bunny trail on, but that's one reason why the high voltage lines that go across the city, those things are up at kilovolt ranges, right? Because you have less amps and less heat for the same work, less resistive losses. And I know if you know about how electrical power systems are run, that there's more to it than just higher volts equals less amps. That's AC, that's something different. Let's not go into it. But that's the gist of it. Okay, so, got all that? Let's keep going. Heat dissipated is a function of the resistance of the circuit. So low resistance circuits won't actually see much difference between high and low voltage. In theory, if you had a zero resistance circuit, well, then the current flow would be infinite for any amount. That's not the point. But the heat dissipated goes up as a function of both the current, it's current squared times resistance. So if resistance is low, then the difference between a higher and a low current won't be, or a high and a low volts, won't be as significant. And the reason I point this out is that if you've got a multi-rotor with 2 inches of wire between the PDB and the ESC, the resistive losses in that wire are going to be really low. And there are advantages to going, say, from 3S to 4S to 6S, but the advantages are not really like in the reduced resistive loss in the wires, because the resistive loss is already so low because it's such a low resistance circuit to begin with. Okay? That's why I point that out. But we are not talking about motors or ESCs at the moment. We're talking about battery chargers. And battery chargers are basically just voltage converters. They take an input voltage and they turn it into an output voltage, and that output voltage is carefully controlled to charge your batteries. And so when we think about battery chargers or voltage converters, one of the key things that we need to be aware of is that watts in equals watts out times efficiency. And the reason this is going to matter is because your battery converter, or your battery charger, is going to be rated at a certain number of watts, and it's going to be limited in the amount of power it can take in and limited in the amount of power it can take out. And as we think about all that stuff, that's going to determine how fast we can charge our batteries and potentially which battery charger we're going to decide to buy. Okay? So let's just take an example here. Here is a Pololu regulator that we all probably have experience with or are familiar with. If we assume that that is a 5-volt regulator and it's putting out 500 milliamps at 85% efficiency, 5 volts times 500 milliamps equals 2.5 watts. we divide by the efficiency factor, we get 2.9 watts. So it is using 2.9 watts. If the input voltage was 9 volts, then 2.9 watts divided by 9 volts means it will take in 0.32 amps or 320 milliamps at 9 volts. At 12 volts, it would take in 260 milliamps. Okay? But again, watts in equals watts out times efficiency. That's the basic equation. So, in summary, as the input voltage goes up, the input current will go down for a fixed output. As the input voltage goes down, the input current will go up, and therefore heat dissipated goes up. And this is significant. One of the things that we're going to see as we get into the the battery charger specs is that the battery chargers, like it's typical to see the battery charger have an input voltage range of between 10 and 18 volts. And its full output power can only be achieved if it's inputting at the higher voltage. At the lower input voltage, it will need higher input current, and too much heat will be generated, and it'll have to have less output. We'll take a look at that as we go in there. But we need to understand that the higher your input voltage, the less heat you will dissipate, and the more power you can output for the same amount of current. This all assumes a switched mode regulator, which is what battery chargers are. But if you had a linear regulator, like on your PDB or something, you should be aware that linear regulators drop voltage just by converting the power to heat. And with linear regulators, the heat dissipated goes up as the difference between the input and the output voltage goes up. So with switched regulators, in general, the higher your input voltage, the less current you will draw, and the less heat you will dissipate. And so it's generally good with a switched regulator to give it a higher input voltage because you'll generally get more efficiency. But let's check the data sheet to be sure. But with with linear regulators, it is always the case that the higher the input voltage, the more heat you will dissipate. And in general, with a linear regulator, you want the input voltage to only be about maybe 1.5 volts to 2 volts, just higher than the dropout voltage, but not much higher if you can possibly avoid it, because you're going to be wasting a lot of power as heat. And just also, perhaps just don't use linear regulators. They have their place, right? They're cheap as beans, as Bruce likes to say, and easy to work with. But they certainly they have to be used in the right place. If you have a large input voltage and a low output voltage, you're going to get tons of heat. You're going to need a big heat sink, and it's just not worth it. Okay? Everything I've said here is a bit of a simplification. For example, efficiency is not a fixed number, but efficiency varies according to the output current and the input voltage. We're going to ignore that for the time being. I just want you to get the concept that watts in equals watts out. So if you're putting out 5 volts, 500 milliamps, multiplied by the efficiency factor, you say that's 2.9 watts, and you know that whatever your input voltage is, you have to have 2.9 watts coming in. Okay? You can't get free energy from nothing. Okay? So if you really want to know about this stuff, check the data sheet from the manufacturer. Well, I see that I'm now 13, almost 14 minutes into this video. So, instead of getting into this awesome spreadsheet that I've made, I'm just going to tease you with it. I'm going to end the video here, and I'm going to put the next batch of content into the next video, because I feel like 15 minutes is a pretty good length for a video, and I feel like we've covered a good amount of information. So, hope that was helpful. Happy flying. See you next time.